Hello guys, we are meeting once again. Our topic for today, it's heat. Now under it, I'll first look at expansion of solids. Now that's what we are going to start off with. That's our topic. It's a very easy topic which you are supposed to get all the marks in the exam. Now under expansion of solids, I think we do understand that what happens with the solids when they are exposed to certain temperature conditions, they tend to expand or they tend to compress. So depending on the conditions. Now, the first important thing that we are going to be looking at, let's look at what we call a linear expansion. Now, linear expansion of solids, it is basically denoted by the symbol alpha. It is denoted by our symbol alpha. So, in practice, our alpha, it has a constant ratio of 1. Now, for linear expansion, the second thing which you need to remember, when you calculate our change in expansion under linear conditions, we say delta L equals to our original length times our coefficient of linear expansion times our delta T, where our delta T, that's our temperature, and then our linear expansion, and then LO, that's our original length. And then how do we get our final length? Therefore, final length equals to a change in length plus our original length. So this is a very simple question. I hope you are going to be following what we are going to be doing. Now, the second part which we need to look at, let's look at area expansion. Let's look at area expansion. Now, you must understand this. Area expansion can also be referred to as a surface expansion. Now, surface expansion can also be referred to as superficial expansion. So these three terms, they mean one and the same thing. Now, our area expansion or our surface or superficial expansion, it is denoted by the symbol beta. And our constant ratio for beta is 2. Now, how do we calculate our change in area? Change in area equals to our original area times our beta into our change in temperature. And then to calculate our final area, a final equals to our original area plus our change in area. So that's how we calculate our change in area as well as our final area. But you must be duty bound to remember how do you find the area of the following shapes. In many cases, they tend to give you a square, and then the sides or the dimensions will be given. And in some cases, they might give you a sphere. So these are a few things that you might need to remember. Formulas for calculating a square as well as a sphere. It's not even that much. And then let's go to our number 3. Number 3, we have what we call our volume. We have volume expansion. Volume expansion can also be referred to as volumetric expansion. Some, they might describe it as the cubic expansion. Others, they denote it as the cubical expansion. So basically these terms are used to refer to expansion that is under volumetric conditions. Now, a volumetric expansion is denoted by a symbol Y, though some books they might write it as an R, and the ratio of our Y, it is constant at 3. So basically, our ratio for alpha as to beta as to volume, it becomes 1 as to 2 as to 3. So how do we calculate then our change in volume? Change in volume equals to our original volume times our Y into our delta T. The biggest challenge which we have here is not on how to use formulas. The biggest challenge that we have is that in the exam, they might give you a linear expansion, but they want you to calculate area, which is to say, if you are given your expansion in linear form, but you want to calculate your change in area, that is where the drama usually starts. I think you will see as we are going to be solving some questions. Now, for those of you who are having a textbook by this gentleman, J.F. de Villiers, I'm on activity, I am on activity, where is our activities? Activity 7.1. Now, on activity 7.1, I will just try to pick one question and then we try to do together, and then you see what are we intended to do. Now, on question number, I'll pick number 8, but I'll pick more questions and then we do them together. I pick number 8 because in many cases they do bring such questions like this under examination conditions. Now, on question number 8, it says a block of steel is 600 millimeters by 400 millimeters and 200 millimeters at 20 degrees Celsius. It is heated to 250 degrees Celsius. The coefficient of linear expansion is given as 12 times 10 raised to the power of negative 6 per Kelvin. Now, I can just try to summarize what we are given here. On this question, our T1 is given as 20 degrees Celsius. So you can change if you want to Kelvin, but you are not compelled. As long as under expansion you do what you want, but if you want, you can change it to Kelvin. And then T2 here is given as, our T2 is given as 250 degree Celsius. And then our linear expansion is given as, 12 times 10 raised to the power of negative 6 per Kelvin. What else are we given? And then the dimensions of the block, the dimensions are given as 600 millimeters by 400 millimeters by 200 millimeters. That's what we are given. Now from there, the question says calculate the increase in length of the longest side. Now, if you look at our diagram here, or rather on our dimensions, we are given 600 by 400 as well as by 200. So the larger dimension becomes what? 600 millimeters times 400 millimeters. But if they said for the smaller dimensions, we're going to say 400 by 200. So for the larger dimensions, we need 600 by 400 when we are looking for our area. But for now, we are calculating the increase in length for the longest side. So this becomes our longest side. Therefore, our change in length equals to our original length times our linear expansion into our T2 minus our T1, or our change in temperature. Our original length for the longest side is 600 millimeters. Our linear expansion is 12 times 10 to the power of negative 6 into 250 minus, but for those who want to change to Kelvin, there's no problem. If you want to change to Kelvin, we say 250 plus 273, we are getting 523 Kelvin minus 20 degrees Celsius plus 273, we are getting 293 Kelvin. So let's get our answer, 600 times 12 times 10 raised to the power of negative 6 times 523 minus 293. I'm getting my answer is 1.656 millimeters. And then number B, the question says, so that's what you are getting in millimeters. If they want you in meters, I think we know what we need to do from millimeters to meters, so it won't be a problem. Number B, they want the area of the longest surface at 250 degrees Celsius. So the first thing that we need to do, let's calculate our change in area. Change in area equals to our original area times our beta into our change in temperature. So here you must be a bit careful. They want the area of the longest surface at 250 degrees Celsius. 250, that's our final temperature. Therefore, our longest sides which we have 600 by 400. So our area now, it becomes original area. It becomes, if we divide by 600 divided by 1,000, changing millimeters to meters. So we have 0.6 times 0.4. So which becomes 0.4 times 0.6. We are getting 0.24 meter squared. So we come here 0.24 meter squared times our beta. Now we have a small problem once again. They want us to calculate area, but our expansion is given in what? In linear form. So what do we need to do there? But beta equals to alpha times 2. So you need to calculate your to times your alpha by 2, because we are changing it from linear form to area expansion. So 12 times 10 raised to the power of negative 6 times 2, which is we are getting 24 times 10 raised to the power of negative 6. Perfect. So we substitute here 24 times 10 raised to the power of negative 6 into our change in temperature. 523 minus 293. 523 minus 293. 523 minus 293. I'm getting something like 230. So it's 523 minus 293. Yes, it's 230. So let's see what are we getting as our answer. 0.24 times 24 times 10 raised to the power of negative 6 times 230. I'm getting my answer as 1.3248 times 10 raised to the power of negative 3 meter squared. Now, they said calculate the area of the longest surface at 250 degrees Celsius. Therefore, A final equals to A original plus our change in area. That's what they need us to do. Original area, we said it's 0.24. Our change in area, it's 1.3248 times 10 raised to the negative 3. So 0.24 plus 1.324 times 10 raised to the negative 3. I'm getting my answer is 0.241 meter squared. Therefore, this becomes our area at 250 degrees Celsius, or our final area at 523 Kelvin. Now, on number C, the question says, calculate the increase in volume in meter cubed. Now, increase in volume, change in volume equals to original volume times our cubical expansion into our change in temperature. Original volume, we can also divide the dimensions by 1,000 because they want the answer to be in meter cubed. So it becomes 0.6 if you divide by 1,000 times 0.4 times 0.2 times. Another small problem, once again, we are given our expansion in linear form, but we want our volume. So therefore y equals to alpha times 3. So our alpha, we said, is 12 times 10 raised to the negative 3 times our 3, our expansion. So we are getting 0.0, or rather not, it's 12 times 10 raised to the negative 6. Yes, our expansion is negative 6, not 3, times 3. So you are getting something like, sorry for this part, so it becomes 36 times 10 raised to the negative 6. So it becomes a normal size. So we have 36 times 10 raised to the negative 6. Our expansion, change in temperature, becomes 230. So let's get our volume, 0.6 times 0.4 times 0.2 times 36 times 10 raised to the negative 6 times 230. So I'm getting my answer as 3.9744 times 10 raised to the negative 4 cubic meters. So this is how you deal with the question or questions of this nature if they come in the exam. So the most important thing is you must remember these terms. For area expansion, if they say the surface expansion, they are basically referring to area. If they say superficial, they are still referring to area. And don't forget how to find the areas of different shapes. Once you do like that, you should be able to survive under examination conditions. And also of importance, remember, in the exam, they will deliberately give you your expansion in linear form, but we need it to be in what? Maybe area expansion or volumetric. Don't forget these few steps. Let's come again in the next 5 minutes or 10 minutes as we do Boyle's law and Charles' law. We are also doing it, Boyle's law and Charles' law, and then we are done. Thank you.